recording on my end.
Oh, okay. We're good. Good evening, folks. Welcome. Thank you for coming in out of bad weather night to listen to why the state of California looks the way it does. My name is Elliott. I'm also the president of Friends of the Arcata Marsh, and we are here to take care of the marsh for the community. As you know, the marsh was built to handle wastewater. It was innovative, the first place in the world, a civic area to treat its wastewater this way, and now it's been copied all over the world. Friends of the Arcata Marsh raises money. We work with the city and do lots of stuff like educational outreach. Tonight is part of our lecture series, the first Wednesday of every month. The next 2 months are going to be students from, I almost said Humboldt State University, Cal Poly Humboldt, and they will be talking about first biology of the marshes, and then again in March, the speaker will talk about fishes of the marsh. So as you know, we have a lot of active research going on here, including Jeff Black's team that works with I almost said sea otters. I'm going to be doing this, it looks like tonight. River otters, you know, we have about an average of 8 river otters that hang out here at the marshes. Usually a passel of females with pups, and the bachelor males migrate around and then come and try to persuade the females. Okay. All right. Well, you are lucky to live in a place called California. Take a look at this map. California is biodiverse, meaning it's a hot spot. All over the world, people come here to see our plant life, our animal life, and the reason it's so biologically diverse is the underlying geology. And we're going to talk about that this evening. But as you can see, there's a lot going on in California. Just for comparison, look at the western United States, and they tend to be boring compared to California. Nevada is completely covered with caterpillars that are all crawling north in the same direction. That's a basin and range province. We're actually going to talk about that tonight. But California has many different kinds of mountain ranges, including the coastal range where you and I are. Volcanoes, we have that great Central Valley, an enormous agricultural influence here in the United States. 3 kinds of deserts. Oh, and I just remembered somebody wanted me to talk quickly about climate and weather as it affects California. As you know, tonight, the weather comes at us from the ocean. So on the coast of California, you get very wet. What happens is the air comes in, and when it hits mountains, the air rises up and it gets colder, which causes the water to condense and drop down on us. The same happens with, oh, I have a pointer. The same happens with the Cascade Mountain Range here that takes sort of the remainder of the water out. And by the time the clouds get over the eastern border of California, they're dry. So we have deserts all down the eastern side of California. These are colder deserts up there, middle level, and then the Sonoma Desert that we share with Mexico. Okay. What did I say? I said Sonoma. Yeah, you guys throw a shoe at me if I screw something up. It looks like I'm going to do that tonight. The last interesting point I want to start with is that plate tectonics describes everything I'm going to talk about tonight. The interesting part of that to me is that plate tectonics is new in my lifetime, right? And I'm young. Ignore the gray hair there. You know, in the 60s, if you had said that the surface of the earth slides around and crashes into itself, people would have ridiculed you. And they ridiculed a guy named Wegener, who came up with this idea and started providing data. They ridiculed him. And then as more data came in, like surveys of the Atlantic Ocean that found a huge mountain range running right down the middle underwater, as the data came in, it became pretty clear that he was right, that the surface of the Earth is broken into plates, and we'll talk about that. So compare California to what it looked like 77 million years ago. Now, notice that North America is in 3 island continents. Appalachia would be part of New England today. And if you look on the West Coast, there's this long, skinny island called Laramidia, and Tyrannosaurus Rex would have been stomping up and down that land, and the other dinosaurs 77 million years ago. Actually, I think T-Rex didn't come along until closer to the extinction, like 68 million years ago. Anyway, if you look at where California would be, can you see the shadow outline there on the map? California is in the water. In other words, it hasn't formed yet 77 million years ago, except for a peninsula that's sticking down from what is now Oregon. Also, there's this shallow ocean in the middle of the continent, and that doesn't exist today. So what I'm going to describe in the plate tectonics is how we lost our ocean. And sure enough, if you're in Nebraska, you can dig up marine fossils, ammonoids, fishes from the ocean, all kinds of weird stuff. So we're going to start there and end up with this. And what I want to cover tonight are all the sections of California, the big landmarks. So before I get to them, quiz yourself. Can you name all the big landmarks in California? Did you know that upper east corner is the Modoc Plateau? Raise your hand if you've driven through there and seen all the lava. Okay, that's a pretty good faction. Next up, we have to talk about the Cascade Mountain Range, talk about Mount Shasta and the other volcanoes. Here we are, the coastal mountain range, basin and range province from Nevada to the Sierras, and then the Sierra Nevada and the Valley. I'll talk about those together. The San Andreas Fault. Most people will know about the San Andreas Fault. Do you know where it came from? It hasn't always been there. And the Grand Canyon and the Colorado River, only because they're close to us and part of this whole system. Okay, I've been putting together what I'm going to describe tonight for decades, just because I love the subject. I was leading a tour in the Redwoods this summer, and a woman asked me, "You must have read Rough Hewn Land." And I said, "What the heck is that?" It was this book. So I bought the book and read it. Everything I'm going to talk about tonight is in this book. And it's worth reading because it's written by a geologist who is a good writer and has a sense of humor. So if you're a book reader, this is a good one. Okay, we're going to start at the Modoc Plateau up in northeastern California. I like to start there because it's formed in a different way from the rest of the volcanoes in California. This is a complicated picture. So you're looking at a map of, on the left there, Washington, Oregon, and Northern California. And right where Idaho and Oregon come together at the southern end, 16 million years ago, 16 million years ago, a hot spot opened up. That is, the earth opened up and out-flooded basalt, lava, and it covered an enormous area of land. All of eastern Oregon is volcanic from this hotspot. And just to remind you, what we want to talk about is there at the red circle. And I'm going to get back to it, but I can't not talk about that pink stripe that says hotspot track. Okay, so imagine this was a movie and the hot spot opened up and this lava flowed out, covering this enormous area of the Western North America. This next slide is showing the brown area, which is that lava. And now notice where that pink arrow was. Look at all those circles. Those are volcano calderas. Every one of those circles is a line of volcanoes that started in eastern Oregon. And now look at the numbers at the bottom. 16 million years ago, this was the first of those volcanoes. 14 million years ago, you had another one. And then those volcanoes just seemed to be crawling across the Western United States and ended up here. Does anybody know about a volcano that's in northwestern Wyoming? Yellowstone National Park. So Yellowstone National Park is the volcano that resulted from all of this. It's a hot spot, and there are other ones on the planet. For example, in the middle of the Pacific Ocean, the islands of Hawaii are a hot spot. And because the floor of the ocean is moving over the hot spot, you get a series of islands that gradually over millions of years wear out. Okay, if you've been to Yellowstone, it's a fascinating place to be, but you're standing on one of the great volcanoes on Earth. The last time it blew up was 640,000 years ago. And when it blew, it covered the Western United States in ash. We're talking an enormous volcano, huge volumes of ash coming out. Okay, finally, we're going to get back to California. And where you see that red circle, 4 to 8 million years ago, the last of those lava flows covered northeastern California. And that's the plateau we call the Modoc Plateau. And if you've ever driven through there, it's amazing. I love it that we have two names for lava from Hawaii. If it's rope-like and smooth, it's called pahoehoe. This will be on the quiz at the end of the night. If you walk on it and it's like sharp glass edges that cut your feet, that's called aa. Some of you already knew that, huh? Aa and pahoehoe. I love those colorful names. Okay, so this is where the northeast corner of California came from. Let's keep moving. We're going to look now for where most of the volcanoes in California came from. And to do that, we have to start from the beginning. So this is a chart. Okay. Oh, I have to click OK. All right. Oh, I should have done that a long time ago. Hold on. Oh, no. There you go. Uh-oh. I think I might be on the wrong slide. We're about to find out. This chart is from the year 2016, and all those colored circles and dots that you see are earthquakes. The different colors represent different intensities, and if you look up at the top, orange and red are the big ones. So you can see a lot of them north of Australia there and some over in Central America. The second thing that jumps out is that all of those earthquakes show a pattern. And it's not snakes under the surface or anything like that. What's happening is in this picture, you can see from the earthquakes how the surface of the earth is broken up into about a dozen major blocks. They're called plates, and we're on one of them. All right, let me see if no, I made a boo-boo. I got to go back. Hold on. There. Okay, so these cracks are where earthquakes happen, but it also shows where melted rocks are coming up from deep in the earth onto the surface, even under the ocean. And to get to the beginning of that, this picture was from the New York Times, and it turns out this year, some scientists did one of those fancy computer models where they try to get answers to what happened in the early Earth. What happened was a planet the size of Mars, it's called Theia, slammed into the Earth. This is 4 billion years ago. And several things resulted from that. Number one, a mess. Lots of parts of the Earth and that planet blew out into space. Number two, both of them melted. The Earth was already hot and melted from other asteroids that had been crashing into it. Remember, this is 4 billion years ago. And then when the dust settled, there's two things that matter to us. And here's the other half of that diagram. That's where the moon came from. So all of these loose rocks that were orbiting around the Earth eventually coalesced and clumped together to form the moon. The second thing we care about is deep inside the Earth, what looks like a couple of red mountains are very dense and melted rocks. And because they're super hot, they're less dense than the surrounding rocks, and that means they start to rise up. And it's that rising current of rocks deep in the Earth that causes the surface of the Earth to break up into those plates. So what these scientists are saying is the computer models have shown that the best explanation for the origin of plate tectonics was 4 billion years ago. Very dramatic. Okay, so now you know where the cracks on the surface of the Earth come from. We're going to focus on how that affects California. This crack, right down the middle of the Atlantic Ocean, is called the Mid-Atlantic Ridge. It's not very creative, but it does describe what's going on there. Notice that the Atlantic Ocean is equidistant from that line on both sides. Doesn't it look like North America used to fit over here? And look at this bump on South America. Doesn't it look like it used to fit there? It did. And it's this mid-Atlantic ridge that separated those continents. Here's why. Because it's called a spreading center, the lava comes up and moves in both directions. More on that in a minute. So for Californians, how does that matter to us? It means that North America is moving west. You have to remember that because it has a huge influence on the formation of everything in California. Oh, hang on. I was going to admit somebody and then I just screwed everything up. Okay. So North America is moving west. That should be fine. We could enjoy traveling over to Japan until we crashed into something going the opposite way on the western edge of North America. This is the floor of the ocean. It's another plate. It's called the Farallon Plate, and it is moving east. So North America is coming west, Farallon Plate going east. There's going to be trouble. And the trouble is this border, the left side of the Farallon Plate, because it's another one of those spreading centers. So here's a diagram of a spreading center. This is the Mid-Atlantic Ridge that's pushing South America away from Africa. And the cause of it is this magma. That red blob there is melted rocks rising up to the surface. And notice that this is the ocean here. So this is all happening on the floor of the ocean. The lava, the magma or melted rocks are rising all along that ridge. And at the top of the picture is one place, at least one place on Earth where the crack in the Earth shows up on land, and Iceland is that country. They get almost entirely all of their electricity from hydrothermal vents. They pump water down into the melted rocks, it comes back up, and they heat all their houses with it. They generate electricity. It's great. Iceland is benefiting from it, but as you may know from the news, the volcanoes are erupting right now on the southern portion of Iceland. Anyway, the magma rises all along that ridge, and that causes the ridge to separate, because as the melted rocks get up high enough, they start to collapse left and right and push the floor of the ocean in both directions. Okay, so that's our spreading center. So once again, North America, notice the red lines are spreading centers off our coast, and those two yellow arrows are showing you that the Farallon plate is going east, North America is going west, and one of the results is volcanoes. And we have volcanoes all up and down North America and South America. So this is a huge volume of melted rocks coming up from underneath the earth. There's a word up there on the screen called subduction, and that's also going to be on your quiz. Subduction is what happens when these two plates collide, and it's right here at the margin where you and I live. You ready? So, to do that, we're going to talk about, I'm going to risk pushing a button. Hold on. Hold your breath. Oh, it worked. We're going to talk first about the Cascade Mountains, which, as you know, have volcanoes in them. Mount Shasta, Mount Lassen. And they come from a subduction zone. All right, so this is a little complicated, but you may already know parts of it. So stay with me, because you're going to get some basic geology here. The huge green line that's bent down in the middle of the screen, that's the floor of the Pacific Ocean, right there. Somehow, the floor of the Pacific Ocean hits North America and dives down. Now, I'm about to talk about why. And the result is volcanoes inland. So the Cascade Mountain Range is pretty far inland from the coast. All of this works together like a gigantic machine, and I'm going to walk you through how it works. To do that, we need to talk about rocks. The most common rock on Earth is peridotite, and I have one here. Can you all see this rock is black and it's not shiny or reflective? This is peridotite. And while it's the most common rock on Earth, at least on the crust, we don't see much of it because almost all of it is in the floor of the ocean. So we don't see much, but everything else comes from this. So this is peridotite, and it's diving down under North America. The next rock to talk about, push a button, there it is. See that thin green line? That's California's state rock. It's serpentinite, and here it is. Notice the first part of the word is serpent. Somebody thought the shiny green surface of the rock looked like the skin of a snake, and so they named it serpentinite, which is colorful. Serpentinite is the same thing. Serpentinite is peridotite, but something happened to it. As serpentinite followed the subduction zone down deeper into the earth, it started getting hot and a lot of pressure. And so ocean water got pushed into that black rock and turned it green. So this is hydrated peridotite. This is water forced into that black rock. And that's interesting. We all love our state rock. But the effects of that are enormous. Listen to how serpentinite changed everything, because the next thing to happen is serpentinite again. As it kept flowing downhill here, it got hotter and more pressure. Look at this. all of this earth is stacked up on this area. And as you go deeper into the earth, it gets hotter. So there's heat, there's pressure, and serpentinite now is starting to cook. And when it gets to be 500 degrees Celsius, 100 degrees Celsius is boiling water, right? So this is 5 times the heat of boiling water. It's so hot, you would expect it to just turn to steam like it does up here when we're boiling water. But it can't down there because of the pressure. So it stays water, it just increases its heat. And it gets so hot that it melts the rocks around it. Now you see these orange bubbles coming up? We're getting close to the explanation of where our volcanoes come from. It's serpentinite that's releasing its water, melting the rocks around it, and because they're melted and liquid and less dense, they start to bubble up toward the surface. Some of these bubbles stay underground. They don't make it to the surface. And if they do that, if they stay under the surface of the earth for millions of years, they start to crystallize. So similar minerals, quartz, feldspar, micas, if you've ever seen granite, those minerals cluster together and form crystals. And what I have right here is a little chunk of granite. This is the guts of the Sierra Nevada mountains because the melted rocks rose, stayed underground for 100 million years, and they were able to form these large crystals. They're beautiful. And there's a whole geology lesson about what each of those crystals are. Okay, that's granite. If the granite makes it to the surface and blows out of a volcano, it cools off so quickly that it can't form those crystals. We call that lava. And you've seen these red rocks around, I'm sure. People buy them to put in their barbecues, right? Because they take up the heat and release it evenly. And so people like that for cooking their T-bone steaks. This came out of a neighbor's yard with permission. So these rocks tell the story of how the floor of the ocean dives under North America and creates the mountains that tend to explode. And as you know, in 1980, we had a volcano in Washington State blow up, Mount St. Helens. And our volcanoes in California, Lassen and Shasta, are not dead. They're still alive. They will blow again. They've blown in historical times. They will blow again. We just don't know when. There's a lot of that going on in geology. Okay, this is a geological map of California. And you can see the white area there are the Cascade volcanoes that I just described. The red zone is the Sierra Nevada mountains. And remember, this is where the granite stayed underground and crystallized. And then the yellow area is the Great Central Valley, and it's connected to the Sierras. And we'll talk about that right now. So let's take a close-up view of the Sierra Nevada mountains and where they came from. The pink area is an enormous blob of granite. It's called a pluton. That pluton was formed 100 million years ago. This is in the Mesozoic. Dinosaurs were stomping all over the place. And that granite had 100 million years to sit down there and crystallize. All those minerals came together to form that speckled pattern. That blob of granite was horizontal until 10 million years ago. 10 million years ago, another blob, this is that red blob you see on the right side, is another pool of magma that rose up and pushed the granite until it broke. And the eastern side of that block stuck up in the air. So right here, the tip of that rectangular block is the Sierra Nevada mountains. The problem is what you see today is not the way it started out. 10 million years ago, Mount Whitney, the highest mountain in the lower 48, was under more than a mile of dirt. So where did the dirt go? The Central Valley. So all of this was piled up with dirt. And think of what's happened in the last 10 million years. We went through an ice age, and glaciers are very good at carving enormous chunks of rocks out of the mountains. You've had rain and wind and all of the erosional forces that strip down the soil off of the mountains and into our great Central Valley. So over there on the left, you can see the yellow pattern, which is a pileup of dirt that got there from erosion. We're going to come back to this crack in the Pluton in another topic here in a little bit. Okay, so this is the Sierra Nevada mountains and when and where they formed. Let's move on to something closer to home. You and I live in the coastal ranges. The arrow is pointing about where Eureka is, and north of us are the Klamath Mountains, King Range south of us, and so on. So that's what we're talking about. Remember our subduction zone? There was one part I left out, and that's that green trapezoid, right? Here. Wait a minute. This is all working backward. This is I'm testing my dexterity. I'm not going to do that again.
It's a green one, right?
Yeah, that light green blob there. So when the floor of the ocean dived under North America and the ocean floor formed a trench. So anything that was on the surface of the ocean floor and anything that eroded off the land, you know, all our rivers carry tons of dirt and sediments into the ocean. It all piles up in that trench. And then, kaboom, it ends up piled up on the shore, which is where the coastal mountains are. Now, there's something different about these rocks. They don't stick together like that granite does. It's not one solid block. It's called a melange in geology speak. And that means it's made up of all different kinds of rock and soil and sediments and loose stuff that doesn't stick together very well. So let's imagine you work for Caltrans and the governor says, I'd like you to build a freeway, 101, and I'd like you to have it run from Eureka up to Crescent City. If you're in charge of Caltrans, this is a good time to retire. Because as you know, you can't make it to Crescent City without seeing construction. That's because the rain that we're enjoying right now soaks into these rocks and these soils, and the hillsides start slumping. And they're going to do that forever because they're all loose. They're not consolidated. And that loose soil is a disaster if you're a roadway engineer. But it's also part of our diversity. You want to see what I mean? This is inland of the coast. And where you see black blobs, this is that serpentinite coming back to haunt us. Now remember, serpentinite is from the ocean floor. And that rock, when it makes it, because it gets scraped onto the coast here, when it surfaces, it makes a kind of soil that's rich in serpentinite, but plants hate it. I'm going to show you a picture from Canada. And what you're looking at here is a nice clean line between the plants, the very green picture on the left, and kind of a desert scene on the right. That line is a border between a normal, healthy soil and over here on the right, serpentinite. Plants don't like it, and you can tell just by looking at this picture. Did I say this is from Canada? Okay, so why is that? It turns out that serpentine soils are rich in heavy metals. Plants don't like that. It's like toxic. Iron, magnesium, nickel, that sort of thing. those soils are also poor. They're weak in the things that plants want. Fertilizer, like nitrogen and phosphorus and potassium, those kinds of things. So it's rich in bad stuff, poor in good stuff, and plants don't like it. And you can see that here. But remember, these soils have been here for millions of years. So we have a whole variety of plants that got used to these bad soils and made it work. Here comes a picture of that. This is a drawing, and the plants in this picture have decided to make a living where many plants don't like it. For example, look on the lower right. That's a pitcher plant, Darlingtonia. It grows in very wet, boggy soils, and those soils are weak in nutrients. So this plant decided, it doesn't have a brain, but it decided that there must be another way to get what it wants. So inside Darlingtonia is hollow and a pool of water. Insects crawl in there, they get into the water and are digested by hormones that the plant puts out. So the missing nutrients come to this plant from a different direction, from animal digestion. So it's a carnivorous plant. Some of the other plants look like plants that we would see around here. Jeffrey pine, ponderosa pine. You see pine trees that have adapted to these bad soils. Manzanita. There are 54 different species of manzanita in California. If you go to the botanical gardens down by CR, you get a nice sample down there. It's a lovely garden. I particularly like that Bollander's lily there on the left. It's a gorgeous lily. There are several in our area. Kellogg's lily in old growth redwood forest. I saw some this summer.
So both the manzanita family and pine group have special mycorrhizal relationships with fungi.
Yes. The question was, does their success depend on fungal relationship? You know, underground is a whole bunch of mycorrhizal fungi that feed to them. And I don't know the details of how that works with these plants growing on serpentine soils, but it's a great question. I'm going to have to go look that up. Okay, so, yes.
Clarify. So we've all driven up to Crescent City, and we've all, I think, on the 101 South have gone to Fusion Hill, which needed that life.
Yeah.
So my thought was that the 101 is being undermined because of the subduction of the ocean, of the Pacific Ocean plate. It's just kind of undermining the coastline. And did you say that it's not that so much as the whether it's the serpentinite or falling down onto the 101 or the 101 area?
Yeah. So once the coastal range is built, it wants to fall apart again. That's why the freeway is always in trouble. Because it's water. This is like the wettest part of California. We get all the rain, the soils build up as much moisture as they can, and when they're saturated, they start to slump. And so it's no, the subduction brought them here, but then they start to fall apart because of how wet it is. If you put
it's going underneath, like
yeah,
that, like you know, supposedly at the speed that fingernails grow. So
right.
Okay, so it's the rock falling down on
Yes.
the area that's fundamental.
Another way of saying that, if you took the coastal mountains and put them in Nevada, they'd be fine because they're going to stay dry there and not get saturated with water. You could build 101 freeway in Nevada and not have to spend all that maintenance money keeping it in shape.
You know that I think it's called Franciscan.
Yeah.
So my analogy is it's like chocolate chip cookies. It just
Crumbles.
So,
Yeah.
But it's the wet rock over time that just kind of disintegrates and is kind of piled on top over the.
Yeah. Slumping is a good word for that. Slumping and crumbling. Okay. All right. So we're moving away now from the coastal mountain range, and we're gonna swim in the ocean for a bit, because you just happen to live right next to what's called Triple Junction. Can you see that red arrow at the bottom? Mendocino Triple Junction. It's famous all over the world because it isn't North America crashing into the Pacific plate. It's North America crashing into two other plates. And I'm going to point out why it's called Triple Junction. A better way to describe it is it's a mess. It's combat. It's gladiators in the ring. It's a bunch of guys punching each other out. Yes, ma'am.
There's a fourth plate that they just discovered by doing some terrain in Marsh.
Oh, if there is, I don't know about it. The question was, there may be another plate that's not represented in this picture. Unless it's the one I'm right now thinking of, and I'll show a picture later on.
I'm going to say 6 months, but that's been published, maybe around 4 months.
Oh, do you have a name for it? Okay. If it's the old section of the Farallon plate, I have a picture. All right. So Triple Junction right off the coast. Let's talk about that. You'll remember that this crack is a spreading center. This is where the floor of the ocean is spreading apart and pushing Juan de Fuca plate into us, right? So that Juan de Fuca plate is the floor of the ocean crashing into us. This is the subduction zone. That's where that plate crashes into us. And that's what we were just looking at as the floor of the ocean dives under North America. The third part of Triple Junction is the famous San Andreas Fault. And that's south of Petrolia. Petrolia is famous, at least in my mind, because it's the closest chunk of land to this Triple Junction, little old town of Petrolia. Okay, so look what's happening here. The spreading center is the ocean floor splitting apart. The subduction zone is the ocean floor in North America crashing together. The San Andreas Fault, the third part, is two plates sliding past each other. It's called a transform fault. We're going to see more of that in a bit. So what does that mean for you and I? I think you know, I'm seeing smiling faces. You already know. Thank the science world. Thank you to Lori Dengler, who publishes articles all the time in our local paper. This is one of her diagrams. And not only is it beautiful, but it explains a lot. For example, there's Eureka up there. Look how close we are to Triple Junction where that yellow blob is. Once again, all those dots you see of different colors, those are earthquakes. This time, those are earthquakes over a 35-year period. And more details later. But you can see that they're clustered around Triple Junction. It's because Triple Junction is a mess. Look at the poor San Andreas Fault, who's just trying to mind its own business. It comes up the coast, and now all of a sudden it runs into that subduction zone, and it has to take a hard left to go out into the ocean in what's called the Mendocino Fault. Yeah.
The Pacific plate is moving west. The North American plate is also moving west?
No.
No, it's moving east.
No, the Pacific plate here is moving north. But this is misleading because these arrows are showing you that this Mendocino Fault, it's called a right lateral fault. So what that means is if you're under the water, if you're in the ocean walking along on the floor, and you approach this fault, no matter which side you're standing on, the other side is going to the right. So if you're looking north across the fault, the other side is going to the right. So then you cross the fault and look back where you came from, that side is going to the right. So they're moving in opposite directions. But to answer your question, the Gorda plate is part of that old Farallon plate. This is the part that's crashing into us. The Pacific plate is going north, and I'm gonna,
Subduction is what the Gorda in North America.
yes, it's the Gorda Plate, which is part of the Juan de Fuca Plate, which is part of the Farallon Plate. Okay.
Thank you.
All right, so this is a lovely diagram of why we are such a mess, right? We are a mess. We get earthquakes all the time. Most of them you can't feel, but of course, last month we had one, a big one. Did anybody lose any property here? That's amazing. This is a pretty good size earthquake in 2024.
Geology in that whole area south, or it didn't, I don't think it did much up here.
Yeah. Well, I was surprised at that. We're close enough to that 7.0 earthquake to have done some damage. So maybe it was the direction or the depth of the earthquake. We don't know. I don't know. Lori Dangler would know. She's great. I've listened to her talk several times. So one of the problems with an earthquake, and I think everybody here knows this, right, is it can result in a tsunami. So I'm about to enter the public service portion of our talk tonight. And I want to explain why we have to worry about tsunamis. This picture is showing a subduction zone. If you see this gray line, that's the ocean plate diving under North America. What it's doing is scrunching up the coast of North America. See that red bar? That's where the pressure is building up, because the ocean floor diving down is sort of squeezing it back into North America. And then what happens? A day that the big one happens, this yellow star is the earthquake, and that floor that was pinched in now pops up. And look what it takes with it. It's pushing up the ocean water, lifts it into the air, it comes back down, and then it comes crashing onto the shore. How bad will it be? 10 to 100 feet. So I'm guessing this building is, what, 30 feet tall? And we're in a tsunami zone. So imagine enough ocean water coming up here on land to take this building off its foundation and use it to destroy other buildings in the area. That's what we're talking about.
So why is Laurie Digler say that it's going to, that 1700 quake didn't go past Samoa Boulevard pretty much? And that's where they're saying that that's where the farthest the tsunami would go from.
Well, it's complicated is my answer for. She knows a better answer than I do. But in the, go ahead.
Here now.
Oh.
Yeah, and so there was her familiar voice, and she was talking, the topic was tsunamis, and she said that the height of the tsunami would partly depend on what the depth of the ocean was when the rupture occurred. So if it's deeper, then it would be higher.
Yes. Okay, so if you're online and couldn't hear that, a young woman just described a talk on NPR with Lori Dangler today. Wow, what a coincidence. And what Lori Dangler was describing is the complexity of these tsunamis. If the shore, if off the coast is very steep or very shallow, that changes the way these tsunamis build into these enormous waves. And don't forget, you and I are sitting inside Humboldt Bay. So first the tsunami has to come over those dunes at Samoa. And if you can imagine, I heard a geologist one time describing Humboldt Bay as a bathtub with all of that ocean water sloshing back and forth. These are catastrophic things that happen. And tsunamis are scary, not just because of the water. I mean, this is water way over our head and the force is destructive as all get out. But now the water is carrying trees and buildings and cars. It's like an enormous sandpaper scraping itself over the land. You don't want to be there. And let's talk about what to do, shall we? Remember, this is public service in action. So here's a chart Lori Dangler would know all about. When you have an earthquake, especially a big one, look at the top section of this chart. the best advice, and I heard this from Lori Dengler, is to just drop where you are. Don't run outside, don't stand in a doorway, get under a table if you can. But even if you're laying on the floor next to a table, you get some protection, because what you're worried about is the ceiling falling down. Timbers, drywall, glass, whatever's up there is coming down, and you want to have some protection. The middle panel is showing, don't get curious about the ocean. Run away, go to the highest ground. So right now, we're all thinking, where is the highest ground? Where would you go right now if we had a big earthquake? What is it?
Up on G Street, like Wildberry.
Head for the plaza, that's good. If you don't have enough time, I would go to Mount Trashmore. Everybody know Mount Trashmore? It's not very high, but it all depends on how much time you have, and we're going to get warnings. So Mount Trashmore is very close. It's the highest ground here at the Marsh, and it may save your life. And if you get on Mount Trashmore and your feet are getting wet, what do? Climb a tree? I don't know. Okay, the bottom panel is a reminder. Where's what? Okay. Here's a map of the Marsh. You and I right now are here, this little red arrow. I hope you can see it. This is the wastewater treatment plant, right? And if you head to the west, if you know where Clock Lake is, it's the high ground just above Clock Lake. Yes, that was a former dump, Arcata city dump. They formed Clock Lake by scraping mud from the ocean floor and piling it up on the dump. So it's called Mount Trashmore for that reason. Now, as somebody pointed out, it's not very high, so it might not save your life. So be thinking about where is better. It's good to know wherever I live in Eureka, and if you know where the transfer station is, the dump in Eureka, come up Humboldt or West Hawthorne rather. That you can drive up a hill. That's the bluff, and it surrounds the city of Eureka. If you're on top of the bluff, you're good. You're out of the tsunami zone. But if you're down on the coast, like where the mall is, or the low land surrounding Arcata, that's trouble. Don't go to the shore. In the Alaska quake, I don't remember the year, 60s maybe? 64. You guys are good. Oh, really? How high was the tsunami in Trinidad?
Standing there. He was always listening to radio at work and always checking on everything on the coast. That was his thing.
Huh.
And I was on my home, and he just said, jump in the car. And I was like, okay, someone must be hurt. Go right down to where the marine lab is now.
Yeah.
Just there, all there was a house there. So we stood and looked and watched. And it was really quite amazing because instead of this big like wave people imagine, it was like all the water got sucked out all the way to Seal Rock, which I really flushed out. And there used to be seal ants on there. Okay, and then in a few seconds, the whole beach was full of like a super high tide. But it did not pull up the bluffs and it did not catch us. It just was super high tide.
Wow.
And then, and it was around dusk, so we didn't save it. I'm sure it did a few of the ins and outs. But I got an impression that maybe it's not as shallow right there as you think. I think that's what Lori always says, that it matters what the shape of the coastal areas. I mean, Crescent City, we all know, it's very shallow, that whole area, and it just came right in and went a long way and just took out all those buildings.
Wow. Well, I hope the people online could hear that description. We have a young lady here who her father told her to get in the car. They drove out and witnessed the ocean pulling back in Trinidad from the Alaska earthquake.
He was coming down the coast, and he wanted to see it. Well, because he had a fishing boat in the harbor, also, so. That's the concern about it.
How did his fishing boat do? Did it survive?
It's fine, because it was inside the harbor.
Ah.
One time the boat was lost in 65 when there was a big storm that caused certain current that dragged all the moorings out past Trinidad and all that smashed.
Huh.
It survived that.
You know, when I said Alaska, several of you knew the date. Raise your hand if you knew the date of the Alaska earthquake. You guys don't need me, do you? John Muallim has a book on the Alaska earthquake. I understand that there were people on Glacier Bay in Alaska that were very excited because all of a sudden they could see dead trees that used to be on the floor of the ocean because it pulled out so far. And then, of course, bad news, the ocean came back and a lot of people died.
On the south end of Trinidad State Beach, where the Trinidad Head is, every now and then when the ocean scoops out the sand, there's tops of little spruce trees forest right there.
A ghost forest. Yeah, I heard about that. Well, in the year 1700, and somebody knows the date. Does anybody know the date of what happened in the years?
Somewhere thereabouts.
In the year 1700, the entire subduction zone off our coast broke all at once. Huge earthquake. We're talking 9, which means the ground you're standing on is like you're surfing, and it does it for several minutes. I mean, it seems like it's almost impossible to survive. And how do we know the date? Because the people in Japan for thousands of years have been recording all of their earthquakes and tsunamis. Well, in the year 1700, here comes a tsunami that hit Japan, but there was no earthquake. And so for 300 years, the people in Japan have been scratching their heads wondering, where did that tsunami come from? And it turns out it was us. It was our Cascadia subduction zone, it's called, 700 miles long from us up into British Columbia. Yeah.
How did they make that connection between it was us that caused that earthquake? Was it like records in the tree rings? Was it the landscape?
Oh, somebody here might know the answer to your question, which was how did they figure it out? I'm guessing that pieces of evidence would be gathered. Somebody mentioned sunken forests. So the trees die because the land sinks and the salt water kills the trees. You can date those trees, right? And so evidence like that starts to build up, and you could see scientists scratching their heads saying, well, it looks like it could have been around the year 1700. And then the Japanese people say, yeah, look at our books right here. There it is.
There was Indian lore about the earthquake in the sunken forest.
Ah,
And there was a young geologist, and I forget his name, he was a teacher at Humboldt. And he sort of put everything together about the subduction zone. And he, I believe, went to Japan and had them check books, and that's what sort of said, yes, this is more than Indian lore, this is something true.
okay.
And
But he,
the bad part is, the 200 years overdue for the next.
yeah.
Yeah.
Well, that's the next question that all of us want to answer. Well, if there was a big earthquake in 1700, what's the average lifetime of that subduction zone? And somebody said, well, 300 years, right? There are differences of opinion, and I'm no expert on that, but we know it's going to break again. That's the answer that we need to take home. It will break again. Nobody knows when, so it's best to think about it. And there are pamphlets out that'll help you screw your bookcases to the wall and plan your house so that dishes don't fall down in the earthquake, that kind of thing. And if you live in a low-lying, if you live in the bottoms here in Arcata, have a go bag, right? Something that the things that you don't want to lose, take them with you, jump in the car and get the heck out of there, because if there's a tsunami coming, you don't want to take pictures.
All of many earthquakes that you showed us in a previous slide. So are they kind of, 1700, it was a kaboom, giant. But all those many earthquakes, is that not just like almost like a pressure cooker, just a little bit release, over a long period of time?
Well, yes and no, because it's complicated out there. Some of those earthquakes are close to the surface. Some of them are 20 or 30 miles underground. Some of them are north, some of them are south, some are at the spreading center or the subduction zone. So they're all different kinds of things. And people wonder, well, if we have a little earthquake, could that compel the whole subduction zone to break? And as far as I know, there's no evidence that it works that way. But who knows? That man knows. Ah, okay.
The earthquake, I think it was 7.1 on your chart. It was offshore patrol, triggered a lot of stuff. And that led to a meeting a couple days after the fact, over in the courthouse. I walked in spite of the Brown Act, there's all 5 supervisors, all sorts of department heads, and I'm told, no, it's okay. We're being addressed by the U.S. Geological Survey. We don't know whether that was the big one or the precursor to the big.
Yeah.
Well, if it's the precursor, what are we supposed to do? Well, you're supposed to get everybody above elevation 200 or something, which Arcata, Eureka, a little bit of McKinleyville, down toward Lolita and everything. You know, we're talking 30,000 people.
Yeah.
And, you know, so how long do we tell them to move to high ground? Well, we don't know. So we said, how about we wait for it to hit and then we'll make sure that they move.
Yeah. For those of you online, we're having an interesting discussion from a public works gentleman about how the last one behaved. And even though our response to the 7.0 earthquake was imperfect, it was less than perfect, it did serve to remind us all where we live and that a bigger one is coming sooner or later. And if this one didn't work very well, let's find out why not, and then make sure that when the big one hits, we're doing better. So thank you for that. Paul, yes.
Lori, she wrote an article right after the 70s. That the biggest mistake that everybody made was getting in their car, driving. Because we ended up with total traffic jam in the meantime. And nobody could move. She said, don't drive, run, or walk towards high ground. Of course, I'm thinking the people on the bottom don't have a chance. There's no way they can walk to anything in a reasonable amount of time.
Yeah. Okay. We have more testimony from Lori Dengler. The number I'm remembering is 15 minutes. We'll have, when you feel the earthquake and you can stand up, you have 15 minutes to get the heck out of here. And as you heard Paul say, walking is probably safer. I needed to be downtown. I don't remember why. I'll have to ask Meredith. I had to be in Old Town Eureka just as the entire universe of automobiles was coming the opposite way. And the tsunami, as you guys know, the tsunami did not cause any damage, but it was a great practice session for us, wasn't it? We did have one, 3 inches tall. Okay. Cause for celebration there.
Yeah. In a previous slide, the uplift of the ocean means uplift of a tremendous amount of water. So if it was shallow, it wasn't shallow.
It's one of the variables, yeah. Okay, let's move on so that you can go home before midnight. The next thing we're going to talk about is the Basin and Range Province. And remember those little caterpillars crawling north in the state of Nevada? Well, we've got our own. Look down south there where Death Valley is. We've got Basin and Range all along the eastern edge of California. So I need to describe what that means. What is Basin and Range and what caused it? Here's what caused it. Remember our friend, the Farallon Plate? There it is. Here's the subduction zone of the ocean floor diving under, and most of them around the world just keep going down. Ours did not. There was something pushing up from the bottom, and the term used for it is, of course, flat subduction. So because the Farallon Plate stayed underground like a submarine and just kept going horizontally, look what it did. It pushed up all of this land, and pushing it up thins it out. It sort of flattens the surface of the earth. Step 2, this is complicated, so I have to explain it. This is a picture of tiny little red arrows. Isn't that lovely? So imagine that every one of those arrows is a geologist putting a sensor on the ground and then very quickly run up to his satellite and watch what happens to that sensor as it moves along on the ground. Each of those arrows is showing you how the land is moving. And it's the what you said earlier about the speed your fingernails grow. But you can see on this picture there's a lot of variation. Where it says basin and range, those are tiny little red arrows, meaning the land is not moving very quickly. But look at the coast. The coast is moving north like it's in a hurry. And so even though the average is 25 millimeters a year, an inch-ish, there's a lot of variation. And then there's something else interesting. So you can see that the coast of California is headed north, but let's go up to Oregon and Washington. Look at this. The arrows are coming back. Why? Why is the coast in the state of Washington going the other way? Very good. That's the subduction zone pushing the land in the opposite direction. So it's not, once again, this is not simple. You need a lot of technology to figure all of this out. What you're looking at is how the Pacific Ocean plate, this is not the Farallon, the Pacific Ocean is hooked into Los Angeles and pushing the coast up. What that does to Nevada is force it toward the ocean. And the effect of that, I already said the Pacific plate is pushing north. The effect of that is this. You're stretching the land on the Eastern California and Nevada. So look at this. The land is flat on the green part, the surface. As time goes on, it's stretching a little more, and now it starts to crack and chunks of rock drop down until you end up where we are today with a series of mountain ranges and land that has dropped into valleys. Here's a picture of what we're describing. This is an artist's rendition of the Basin and Range Province. And if you've driven through Nevada or flown your private airplane over it, you've seen this. So the mountain ranges are called karst, and the valleys are called graben. So this is a karst and graben landscape. And when you look at Nevada or Eastern California, this is what you're describing. For us, Death Valley is the most magnificent valley there is because it's so deep. It's the deepest part of our part of the world. And this young lady up front asked, well, why is it so hot there? There was a picture this summer of 132 degrees in Death Valley. Anybody know? Why is it so hot in Death Valley?
Desert, it's sun, it's protected.
It's in a valley, protected. You get intense sunlight, no cloud cover. All of that plays a role. But the air of the atmosphere is all piled up and pressing down on it, and that creates heat. So the deeper you go on land, the hotter it is. And the most extreme example I've ever heard of was a gold mine in South Africa that's like a mile straight underground. They're still digging gold out of it. So these men that work there wear a t-shirt and shorts and nothing else because they sweat all day long while they're down there digging gold a mile underground. Hot. That's where all that melted rock comes from. Did I get that right? I said
They were there out of nowhere when you told us.
oh, okay. What did I say this time? Shorts. Okay, let's go back to underwear. They are working in their underwear because it's so hot down there. Thank you for that. Okay, the Grand Canyon, right at our southern border. Let's talk about the Grand Canyon. Now you know where the Grand Canyon came from, right? It comes right back to this. There's our subduction zone. There is where it says flat subduction. That's the Farallon Plate, once again, our old friend. And now look up at the top in that pink section. First of all, you see melted rocks rising, those red blobs. Are there volcanoes in the Colorado Plateau? Yes, there are. And so the subduction zone ran all the way to the Rocky Mountains, which were pushed up into the air thanks to the same subduction zone. Now, it might not have looked like it at the time. When the Rocky Mountains were formed, once again, they were covered with lots of soil. They were still mountains, but a lot of erosion has happened since then and produced the mountains we see today. So once again, that Farallon Plate pushing its way underground has pushed up all of the Western United States. And this is an exaggerated uplift picture, but look at that. The Western United States is very different from the Eastern United States, except for the Appalachian Mountains. Anybody know where they came from? When North America crashed into Europe, what was that, 400 million years ago? The Appalachian Mountains were the biggest mountain chain on Earth. And so in that time, in the interval between then and now, the Mid-Atlantic Ridge has separated the land, and all those millions of years, the Appalachian Mountains have worn down to their guts. So they're smooth and they're not high like the Sierra Nevada. They're worn out. You're looking at the insides of the former Appalachian Mountains. But ours are dramatic. How many national parks do we have in the Western United States? It's all dramatic scenery, thanks to the Farallon Plate. Okay, this is Southern California before the Farallon Plate hit. And then the Farallon Plate starts pushing the land up. And can you see a river up there on top of that hill? That's the Colorado River. And it got the name Colorado, which in Spanish means it's either red or tan. I think it's red. It gets that name because it's full of sediment. If we didn't dam it up all the time, the Colorado River is loaded with dirt and sand and silt from the land that it's passing through. Eventually, the land rises, the river cuts down as the land is rising, and what you end up with is the story of the Western United States. Those rocks on the bottom are called the Vishnu schist. It's 1 billion years old. And so all these layers of sediment that are different colors are the history. One at a time, these various piles of dirt got spread on the land, and you can read the history of the Western United States in the Grand Canyon. It's a wonderful, wonderful picture. I was hiking down to Phantom Ranch in the Grand Canyon. I turned a corner, and just to my left in all those rocks, it was just packed with fossils. So, you know, whatever that was, 20 million years ago, there was a lot going on at the Grand Canyon. Okay, finally, we're going to get to talk about the San Andreas Fault and where it came from. You've already had hints. Here's a familiar picture. You'll remember that the red lines are spreading centers. North America is headed west. The Farallon Plate is headed east. But now look at the writing on the left side. 30 million years ago, there was no San Andreas Fault. So what happened? I have a series of pictures. In this one, the blue is the Farallon Plate. You can see the red stripe there that is the spreading center. And of course, the land is the orangey looking color there on the right. Can you all see Los Angeles, that little white dot? That's Los Angeles. And that's where the Farallon Plate got closest to the land 30 million years ago. Look what happened next. 20 million years ago, North America ran over that spreading center. There's evidence from this in the rocks. So remember, the Farallon plate is moving east, but now we're crashing into the Pacific plate and it's headed north. So it changes the dynamics at the border. So what's happening now is, compared to each other, the Pacific plate is going up and North America is going south. Once again, that's a right lateral fault. The other side is moving to the right. 10 million years ago, look how the San Andreas Fault is now spreading, because North America continues to run over those spreading centers, and we're not touching the Farallon plate anymore. We're touching the Pacific plate, which is going a different direction. And then finally, we get to today. So there's a smaller section of the Farallon plate down in Mexico. Actually, it's bigger than our plate. It's called the Cocos plate. Here we are at the Juan de Fuca plate up where we live. And if you can see that M with a red triangle, that's triple junction. And what triple junction is trying to tell you is this is where North America is running over the spreading center in the Farallon plate. So you have to imagine holding your breath for 10 million years, and you can just watch as the San Andreas Fault gets bigger and bigger and bigger, and the subduction zone will disappear. Unfortunately, the way that happens is not smooth and gentle. It happens abruptly in earthquakes and tsunamis and that kind of thing. All right, here's a picture of the San Andreas Fault in the Bay Area. As you can see, that big purple fault line there says San Andreas Fault. That's what we all label the San Andreas Fault. But really, all of these faults, the yellow ones included, are part of a system of faults. So the San Andreas Fault is not just one big crack, it's a whole bunch of them. So we just got in our car and we drove from San Francisco to Oakland across the Bay Bridge. And sure enough, sooner or later, we're going to drive across the Hayward Fault, one of those yellow lines. They all can produce their own independent earthquakes and problems. But if it ever happens all at once, the Bay Area is going to be a big mess. Okay, we're almost finished now. It turns out there's another big crack, not just the San Andreas, there's another one. Did we have enough trouble? We didn't need another one. There it is. On the far side of the Sierra Nevada mountains is a huge crack called Walker Lane. I don't know the origin of that or who Walker was, but let's take a look at that Walker Lane and where it came from. If you remember the underground granitic pluton that formed the Sierra Nevada mountains, well, there was a mess of magma that broke it 10 million years ago, right there, and it formed, not only did it push up the Sierra Nevada mountains, but it formed that big crack that runs all the way into Idaho. Well, that's interesting because now geologists are prognosticating. They're trying to figure out what's going to happen to us in the future. And there are three scenarios. Here's one. This is the one you've probably heard of. If the San Andreas Fault continues doing its thing, this is Los Angeles that just moved up in San Francisco's neighborhood. So we can wave across a little bit of water there at each other and say, I think since I live in Los Angeles, I think we're going to be a different country. So we can argue about that in 10 million years. Some geologists say maybe not. Maybe item number 2 is the Walker Lane. And look at this. It comes up the Bay of California up to the far side of the Sierras and cracks north. In this scenario, all of California becomes an island. It's possible. I don't know which is going to happen. And then there's one more. remember how we thinned out the soils in the Basin and Range province and they got kind of skinny? Well, what if it breaks there? That would be kind of like what's happening in East Africa right now, right? Down not the center of Africa, you got to go a little east and there's a huge rift zone. All of the big lakes in Africa are in that rift zone. Africa is in the process of splitting apart. That could happen here in our Basin and Range province. And there would be some poetic justice to that because we used to have an ocean in the middle of the continent. So this would just be bringing it back. I don't know how to put bets on which way this is going. And how would you collect anyway? Okay. That was a lot of information. So this, once again, the idea for this came from Lori Dengler, who said, well, you got to look up a video by Dr. Tanya Atwater. Uh-oh, I have to close out the slideshow to get this video to work. Stop. There we go. All right, so I'm going to click on it. And what you're about to see is everything I've described in motion. Was that an earthquake? Okay. So what I want you to notice is down by Los Angeles at the southern end of California, look how see those red lines? That red line is just about to touch the land. So this video is going to start, this GIF is going to start right as we're overrunning the Farallon Plate. Here we go. So there it is. It's touching land. We just ran over the Farallon Plate. And now look at the San Andreas Fault starting to move up the coast. And down here in Southern California, there's a chunk of land that's twisting. Did you see it turn? Yeah. And now Triple Junction is up where we live. Okay, this is going to start again. So look at that again. We're just about to run over the Farallon Plate and create the San Andreas Fault. And now look up north. Look at the state of Nevada. It's skinny. And as the brand new fault zone starts to push on the edge of California, look at Nevada expanding. So that's the land stretching out. Nevada is now twice as big as it used to be 30 million years ago. Okay, thanks to Dr. Tanya Atwater for that. All right, I'm going to end with a little exploration of Southern California. So this is another picture of all the earthquakes, this time in Southern California, and you can see a blue line running right through the middle where it says Los Angeles, right? What's going on there? Well, let's go to another slide. Oh, before we move on, this is that little chunk of land that was turning, it was spinning around. If you ever wondered why the transverse mountain range is going the wrong direction, it's because it's a kind of a micro plate that turns all by itself. It's a mess down there. But oh, you've driven in Southern California. All right. A crucial part of the San Andreas Fault in Southern California is this. Look at how it bends from south to north. That big body of water is the Salton Sea. And look how the San Andreas takes a big bend and then heads up in a straight line towards San Francisco. That big bend is a problem because remember, this fault wants to slide past, both sides sliding past each other. And they can't do it there because it's pushing into that bend. And so the pressure builds up and it builds up and it builds up until all hell breaks. Can I say hell? All right. All heck breaks loose in Southern California. So you wonder, well, how long has it been since a huge earthquake hit down there? Last significant earthquake just above Los Angeles was 1857. This is from the University of Southern California. The last one by the Salton Sea was in 1690. This is when Catholic priests were marching up and down the coast, causing trouble with Native Americans. Okay, so that's Southern California. By the way, that Big Bend, that's where the Pacific Ocean is hooked in. Imagine Mr. Pacific Plate hooking its shoulder into Los Angeles and pushing the whole coast of California up.
Well, we qualify as a like big earthquake, because also like the Northridge earthquake was like pretty nasty, but it's not listed out there.
Yeah. The question is, what about the Northridge earthquake? Well, according to this diagram, that wasn't big enough to qualify. That's where Paul here teaches or taught. You're retired now. You still get money from him? That's a good deal, man. Well, I got my degree in biology from Northridge, and when I was watching the television after the earthquake, oh my God, that's the chemistry department on fire. It was a big earthquake. Parts of the freeways collapsed. So I don't know what the criteria were for this diagram. Yeah. So 6s and 7s probably don't count, which is a scary thought, because what is a significant earthquake? It's going to be a disaster. Freeways dropping everywhere. Houses, buildings falling over. Lori Dengler said 90% of us will survive the big one here. Will survive. Yeah. So it doesn't have to kill everybody, right? Right. Thank goodness for lumber construction, because our buildings flow. I live in a house in Eureka that was built in 1898, and it's ridden through all of those earthquakes. When I bought it, I did jack it up and pour a concrete perimeter foundation. That's really expensive. Don't do that. No, do it if you can, because it's more secure. And then sure enough, 2 blocks from my house in 2020, no, it was 2010 when we had an earthquake, there was a house on Poston Pier. It jumped off onto the ground. And the woman that owned this house didn't have insurance, right, to recover it. So she didn't know what to do. She sold the house eventually as a project to a guy in construction, who then did jack it up, poured a concrete foundation. He was in the process of saving this house when some homeless people built a fire under it and burned the house down. But things like that tend to happen around here. Wasn't there a Catholic church right up at the cemetery here in Arcata? Same thing that burned down. All right, a little side story. Let's get back to the topic here. Bye. Thank you for coming. All right. It's time to talk about where we live again. And this is approaching the end of the talk. So here's Eureka, right? We had one in 2010 that was 6.5. 2020, we had a 6.4. And of course, we can't forget last month when we got our 7.0. So remember that Lori Dengler picture where there's a big cluster right here at Triple Junction. That's where you chose to live. So the next thing is, oh, wait a minute, what's a dragon doing up there? And where's it going? Well, a dragon is the Farallon Plate. So the question is, where did that fire-breathing ocean floor go? What happened to it? Did it just crumble after we ran over it? Well, here's how you find out. Geologists plant sensors all over the place. And the mountains you see on the right, that's the Wasatch Range around Salt Lake City, Utah. So we've got sensors all over the Western United States. And every time there's an earthquake, you can see the earthquake down there in the lower left. When there's an earthquake, it sends 2 different kinds of signals, a P wave and an S wave, which are vibrations kind of in different directions. And when those waves hit these sensors, all you have to do is plug in your magical computer to make sense of it. And what you get is a picture of what's going on underground. Would you like to see what happened to the Farallon plate? Hold on your seat. This is magnificent. You can see the coast of California up on the surface of the earth there in red. And then somebody took a big knife and cut a slice out of the mantle so that you could see down to the center of the earth. And this blue stuff is the Farallon plate that has finished its subduction and is now down toward the center of the earth. The amazing thing is it hasn't melted yet. It's very hot down there. It hasn't melted and come apart and disappeared yet because it's so dense and it started out cold, right, as the floor of the ocean. So it's still underground. I find this to be just the most beautiful thing. It's like our story continues, right? The Farallon plate is still down there. Okay, we're going to wind up with an expansion from our local neighborhood right there to the rest of the world. What you see here is a color-coded diagram of all of those dozen or so major plates on the surface of the earth. You can see that our plate, the North American plate, is the color brown. And if you look at the Juan de Fuca plate right offshore from us, and now go down to Mexico, and you can see the Cocos plate. The Cocos and our plates used to be combined into the Farallon. That was your quiz. And now the middle part of the Farallon plate is gone. So let's look around the world at 2 or 3 examples of how interesting this gets. How about this one? The Indian plate, the country of India, subcontinent, used to be attached to Antarctica at the South Pole. I don't know that it was at the South Pole at the time, but it separated from Antarctica and it got on like a railroad track and has been moving fast and up north until it crashed into Asia and is still moving in that direction. In other words, the highest mountain range in the world, the Himalayas, have fossils of ocean creatures up there at the top. And those mountains are still getting bigger because India is still crashing into it. Well, that's fun. Let's go over to the opposite side of the Pacific plate and look at Japan. Japan has more earthquakes than any other place in the world. And it's interesting to explore why. Remember our North American plate? Well, look at a little corner of it poking down here. And there's Hokkaido, the northern island of Japan, on the North American plate. No wonder we like the Japanese people. We have the same home. Well, then look down at the South Islands. They're connected to the Eurasian plate. But we're not finished. Here's the Pacific plate going in that direction at this part of the world, crashing into those other 2 plates. And then this red plate is the Philippine plate where the Philippine Islands are. So poor Japan has 4 plates crashing into each other and arguing over who's going to cause the next earthquake and tsunami. And as you know, right at the tip of that arrow on Honshu itself, the big island, it wasn't very long ago, you guys would know, what was the date that they had their big earthquake? You're mumbling.
New plants got rid.
March of
2013 is what I'm thinking.
somewhere between 2011 and 2013, they had a big one. And if you remember, not only did they have an earthquake, but the tsunami came in, and Japan has a record of being one of the most advanced countries for their technology, right? They had 3 nuclear power plants on the coast right next to each other, and nobody anticipated what this tsunami was going to do, but it destroyed the generators. And before you know it, there was a buildup of hydrogen inside the container shell. and their nuclear power plants blow. They're still cleaning up that mess. And so there's lessons there for the rest of the world. Okay, now we have to think about this and that and all of the things that went wrong there. So Japan is the earthquake capital of the world because there are 4 plates crashing into it. And now comes the sad story of Indonesia. Look at this mess. This was 2004. We just had the 20th anniversary last month. There was a magnitude 9.1. We haven't seen numbers this big before tonight. 9.1 and 200, the estimate is 230,000 deaths from the earthquake and tsunami. This was on the island of, just offshore from the island of Sumatra. And when the tsunami came in, not only did it overrun that country, but all around the Indian Ocean. Even on the far side, these tsunamis just kept washing back and forth, destroyed villages. There's a picture of a man standing on household furniture, moving along like he's on a river, and he's completely surrounded with people's houses and cars and what have you. And that thing just swept through there and wiped out 250,000 people. And the folks that do this kind of study are saying this is an undercount. If anything, the numbers are much bigger. You want to guess how big that fault zone is around Indonesia? 700 miles, sound familiar? All right, well, we can't help looking up here at our little corner of the world and knowing that the Cascadia subduction zone is about that same length, or it's close enough that this should be a lesson to us. And so when you hear people, there's a pamphlet out there, and Lori Dengler had a part of it, of developing it. Get that pamphlet. Walk through your house as you turn the pages and look at every little section of your house. What can you do to prepare? What can you put in your go bag? And even if it doesn't happen in your lifetime, you have friends and family and property and cars and all of that kind of stuff. It's a lesson for us that we live in a world that is dynamic. It's a wonderful world. We wouldn't be here, right? It's a wonderful world, but it's dynamic, and there's a lot of energy behind these forces. Okay, on that happy note, we did it. You sat here through the birth of California. Thank you very much. Question?
The Yellowstone volcano, the super volcano kind of thing. Well, that was the top of that chain of the volcanoes that you go from Modoc. There was a whole bunch of them.
Yeah.
So the plate was moving underneath that hot spot.
Ah.
So why did Yellowstone stop? And why does it keep making volcanoes?
The question is, why is Yellowstone National Park parked in northwestern Wyoming? Why doesn't it keep moving?
Yeah.
And the answer is, it is. Yeah. So it started 16 million years ago in Oregon, and now it's marched to Wyoming. Come back in 16 million years, and it's going to be in the Dakotas or wherever. And as you said, it's because North America is moving in the opposite direction. Yeah. Any other discussion? Yeah. Yes, ma'am. Caroline?
Yeah. Dr. Under, does that Yellowstone underneath, like if that is melting it and throwing up?
No, they're different causes. Yellowstone happened because of that freak explosion of a hot spot, but the subduction zone is sort of an independent thing. And the best example is Hawaii, because in the middle of a plate that's normally stable, here comes those islands. Yeah. Well, what caused the hot spot originally was that planet Theia that crashed into us and left hot melted rock that keep bubbling up to the surface.
Thank you.
Okay. Thank you all for your attention.